Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study lecture on measurement of fluid level. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? Question number four, how to learn the knowledge from this course. Let me start with the quick review or overview about the answer to question number one, which is about why to study this course. By now, you should know that our mission on Earth include to understand the world and to change or to improve the world, all right? Then how to understand the world? The answer is to discover knowledge in the physical world. Then how to discover knowledge in the physical world? The answer is to make use of sensory data. Then how to obtain sensory data? The answer is to use measurement and the sensing system, all right? Then how to improve or change the world? The answer is to invent smart machines, smart product, and the smart system. Then how to invent these smart products, smart machines, smart system? The answer is to incorporate closed-loop feedback control system inside the design of these smart products, smart systems, smart machine, etc. All right? Then what is a closed-loop feedback control system? The answer is a closed-loop feedback control system is a system which includes three basic building blocks or three basic building modules. One of them is the sensor. Therefore, this course is extremely important, okay? Not only for industry and also for our daily life in the society. And for example, from this slide, you will understand that the future city may include smart parking systems, smart street lighting systems, smart home systems, smart buildings, smart environmental system, and also smart healthcare system, etc. And in addition, future city may include the deployment of Internet of Things. Inside the Internet of Things, one of the two major devices is a sensor. All right. Then the second question that you may have in mind is about how to study this course. My recommendation to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will ask yourself like these four questions. Question number one, who are the user? Question number two, what are the needs from this user? Question number three, what should be the functionality of the product or system that you are going to develop in order to meet the need of this user? Question number four, what should be the solution behind the design of your future system and the product, etc. All right. So the answer to question number one should be quite straightforward to you, because this user include human being, include smart products, smart machine, and the smart system. All right. Then answer to question number two should be obvious to you as well, because all these users need to have sensory data. All right. Then what should be the answer to question number three? The answer depends on the specific need or specific nature of the user. For example, smart vehicle may require a certain type of a sensor, and the smart robot may require another type of sensor. All right. Then what should be the answer to question number four? The answer is to study well this course. At the end of the study of this course, you will know the solution behind the design of popular sensor in electric domain, magnetic domain, environmental system, and intelligence system. Right. So what are you going to study from this course? Basically, you are going to study the basic principle behind the design of a popular sensor. in electric domain, magnetic domain, environmental system, and intelligence system. In addition, this course covers the basic detail about the physical world, the basic detail about the conceptual world. Also, this course covers the basic knowledge for you to cope with randomness, and this course also covers the basic knowledge for you to understand the phenomenon of fuzziness in conceptual world. All right. Then the fourth question that you may have in mind, okay, is about how to apply learned knowledge from this course. Basically, you should be able to apply learned knowledge to guide the design of your future sensor or your future measurement and the sensing system. All right, and the design basically will follow these two steps. Step number one is to transform the value of a physical quantity on the measurement into readable value. The step number two is to calibrate the sensor or calibrate the measurement and the sensing system. In this way, the output from your sensor or measurement and the sensing system will be exactly equal to the value of a physical quantity on the measurement. In addition, the unit of a measurement assigned to the output is exactly the same as the unit of a measurement from the physical quantity on the measurement. All right. Then for step number one, basically you may face two situations. One corresponds to the case in which it is good enough for you to make use of a front-end sensing element in order to transform the value of a physical quantity on the measurement into readable value. However, in most cases, you may face the second situation in which you have to make use of both front-end sensing element and the back-end sensing element. All right, so this slide basically gives you the general guideline for you to apply, learn the knowledge from this course. Okay, so now we are ready to move on to study today's lecture. Okay, today's lecture is about the measurement of fluid level. All right, so fluid level is one of the important parameters inside the fluid supply system, and you understand that the environment, okay, is very important, okay, to the quality of a human being's life. For example, we need to have the supply of thermal energy or other type of energy. We need to have a supply of oxygen. Without the oxygen, we cannot survive on Earth, right? We need to have a supply of water. We need to have a supply of food from the environment, all right? So in terms of level of importance, so you understand the supply of energy has the #1 importance, because without the energy or without the extremely high level of energy, we cannot survive on Earth, all right? So we can only survive for a certain number of seconds. For example, if the temperature reaches 1,000 degrees, or the temperature reach negative 200 degrees, all right? So within a certain number of seconds, then we will disappear, all right? And without the supply of oxygen, we can only survive for a certain number of minutes, right? Then without the supply of water, we can only survive for a certain number of hours, right? Then without the supply of food, we can only survive for a certain number of days. All right, so now you understand, okay? The supply of water is very important, and the inside the water supply system, fluid level is one of the important parameters, right? So we need to know, okay, the physics behind the fluid level, and also try to understand the basic way for us to determine the value of a fluid level if we know the value of a related parameter, all right? But our focus here is to study the physical principle behind the design of a measurement and the sensing system for fluid level, all right? So let's start with the study of basic physics behind fluid level, right? So first question you may have in mind is about what is a fluid. So basically, fluid refers to any substance which could undergo continuous movement in the form of a flow. All right, then in this case, immediately you understand only material in the state of a liquid or state of a gas could produce a continuous movement in the form of a flow, right? So here you see two animations. First animation is about the flow of water, and this animation basically showing you the flow of air, okay, or gas, okay. And in practice or in theory, the fluid could be classified into two categories. One is called as a Newtonian fluid, another is called as a non-Newtonian fluid. But in order to understand this classification, you need to understand, okay, the meaning of a shear stress, shear strain, and shear rate, okay? So then this slide basically help you to understand, okay, this terminology. For example, if we have applied the force which is parallel to the surface of a fluid, then this applied force will make this column of a fluid to undergo deformation or movement, and this movement is similar to angular motion. Therefore, theta I divided by I is a kind of the angular displacement, right? So, and the angular displacement divided by time is for angular velocity, right? So then this is called as a shear rate, okay? And the shear rate is also called as a rotational speed of the fluid, okay? Due to the applied force, which is parallel to the surface, all right? And then what is a shear stress? So shear stress is equal to the applied force parallel to the surface divided by the area of the surface, all right? So these are the definition of these two technical terms. And this picture also showing you the meaning of shear stress and the shear strain, okay? So shear strain is like the angular displacement, in this case, theta x divided by L. So it is equivalent to theta I divided by I. And the shear stress is equal to the applied force, which is parallel to the top surface, divided by the area of the top surface, all right? Then with these two terms, if let's say we have a fluid which demonstrate this behavior, so it means the relationship between shear stress and the shear rate is linear, okay? Linear means inside this space and these two parameters follow a straight line, okay? So then you see this is a straight line, this straight line. If the fluid follow this kinds of linear relationship, then this fluid is called as a Newtonian fluid, okay? If a fluid does not follow such a linear relationship, then it is called as a non-Newtonian fluid, okay? Now you understand. And actually, all your water, chemical, okay, and our blood basically fall into the category of Newtonian fluid, all right? Then for non-Newtonian fluid, example includes ketchup, includes cream of milk, etc. And interesting things for you to know about the non-Newtonian fluid is the ability for us to walk through the surface of such fluid without sinking inside the fluid, all right? You can also use water and corn flour, okay, to produce fluid which belong to the category of non-Newtonian, right? And this animation showing you that actually we can play the football on the surface of a non-Newtonian fluid. Then in this case, you can imagine that the physical behavior of a new Newtonian fluid is like grass, because on the surface of a grass we also play football. Therefore, you can start to think about this question. Okay, is grass a known Newtonian liquid or not? All right, so you can start to think. All right. As I mentioned earlier, water supply is extremely important to human beings' life on Earth. All right, so therefore we need to have a water supply system, and actually water supply system consists of two parts. One is water storage, and the second one is water distribution. So the storage will make use of a tank, and the distribution will make use of a pipe or network of a pipe. All right. So for this lecture, so we focus on the study of measurement and the sensing system for fluid level, because fluid level is the most important parameter for the water or storage, or for fluid storage. All right, because we need to monitor this very important parameter. And this picture basically showing you we need to have a water storage tank on the roof of the building, on the roof of the house, and the roof of the building, and the roof of the factory, etc. So you see, water supply not only important to human beings' life, and also it's very important to the operation of factory, operation of school, hospital, etc. Right? And then this video we are showing you different type of storage tank in the society, in industry. Then based on this A type of storage tank, more or less you can imagine, okay, the type of fluid needed to be stored, okay, for us to use, or for industry to use, all right? So basically there are A type of storage tank. Type number one. Number two. Type number 5. Number 6. Type number 7. Type number 8. All right, so that should give you overview about the major type of tanks used for the storage of fluid such as water, oil, or chemical, etc. All right, and inside the tank of storage of fluid, we need to know this important phenomenon, which is called the production of buoyant force. Okay, and buoyant force is equal to the weight of a displaced liquid. For example, if we place an object, a solid, inside the fluid, okay, then this solid will displace a certain amount of fluid. All right. So then in this situation, if we collect all the displaced liquid and just know the weight, then actually this weight is exactly equal to a force acting on this solid in the vertical direction. All right, and this force is called as buoyant force. Okay, so and this buoyant force is exactly equal to the weight of displaced liquid. Okay, so this is a very, very important phenomenon, and actually we can apply this physical phenomenon to guide the design of measurement and the sensor system for fluid level, right? And among the water supply system or fluid supply system, because fluid supply system include fluid storage and the fluid distribution. And the fluid level is one of the important parameter. So therefore, we need to know what is liquid level, then how to measure the fluid level. All right, so this video basically give you a rough idea, all right, about the answer to this question, what is the fluid level, and also give you a rough classification, okay, among all the sensor for the measurement of liquid level, right?
To the level zone, a Flowline video training series. This is lesson 1. What is liquid level? Liquid level sensors measure or detect the presence of liquid held in containers. Common liquid types include chemical, water, wastewater, and oil. A level container can be anything that holds liquid, such as a tank, sump, or pond. There are 2 basic types of liquid level sensors, continuous and point. Continuous sensors measure level within a specified range and provide a 4 to 20 milliamp signal output that is proportional to the measured level. These sensors are called level transmitters and are typically used for inventory and process monitoring. Point sensors detect the presence or absence of liquid at their point of installation and provide a switch output that indicates their wet or dry status. These sensors are called level switches and are typically used for basic alarm and control functions. This concludes lesson 1. To the level.
Right. So this video basically give you a rough idea about the liquid level and also the classification of liquid level sensor. Okay, so there are 2 types. One refer to the sensor which will output continuous value, okay, of fluid level, and the second type of sensor will just output discrete value, okay, which correspond to a discrete value of fluid level. All right, so therefore it is quite important for us to understand a little bit the basic physics behind the fluid level. All right, for example, within the same fluid system, okay, and if this system is open to the air, then the pressure at the same level will remain the same. Okay, so inside for example, in this case, tank A, tank B belong to a same fluid system, so therefore at the same level, okay, the pressure will be the same. Okay, so in particular, at the level of a fluid surface in tank A and the fluid surface in tank B, the pressure will be the same. When the pressure is the same, it means what? There's no flow. Okay, so the pressure could be considered as a kind of a potential. For example, in electric domain, we have a voltage. So voltage is also called as an electric potential. All right. So when there's a voltage difference, then the difference in voltage will create flow of electron. All right. Then for thermal energy, temperature is also a kind of a thermal potential. When there's a temperature difference, then there's a flow of heat. Then for the fluid system, okay, the pressure is kind of a potential. Okay, when there's a pressure difference, then pressure difference will produce a flow of liquid or flow of fluid inside the fluid system, right? So this is a very important phenomenon. Also, it is extremely simple, all right? So if we have 2 separate fluid systems, then at the same level, the pressure may not be the same, right? For example, in this case, tank A, tank B are separated, right? So at the same level in tank A, the pressure will be higher than the pressure at the same level in tank B, all right? So therefore, the fluid level in tank A could be different from the fluid level in tank B. Okay, so this property is quite important for you to know. Also, it's extremely simple, all right? And we can consider pressure inside the fluid as kinds of potential, okay? And when there's a difference in potential within the same free system, right? If you have a difference of pressure in two separate free system, then there's no flow of free, right? So within the same free system, when there's a pressure difference, the pressure difference will produce flow of free, okay? So pressure is something like voltage for electron, or heat or temperature to heat, because when there's a temperature difference, then the potential, the difference of a temperature will create flow of the heat, okay? So within the same free system, when there's a pressure difference, then such a pressure difference will produce flow of the fluid, right? So this is a basic physics behind the fluid level, right? Okay, so that should be good enough for you to know, okay, the basic physics behind the phenomenon of fluid storage, right? So you understand the fluid level is a very important parameter, okay, for the storage of fluid, okay. Now we move on to know, okay, how to indirectly know the value of a fluid level inside a tank, or how to directly measure the fluid level inside a tank, all right? So indirect measurement means by computation. By computation means if we know the value of a related physical quantity, then we should be able to calculate the fluid level, all right? So that is an indirect measurement. However, our focus in this course is on the study of the physical principle behind the design of a direct measurement and the sensing system for fluid level, right? So let's start with indirect measurement by doing computation. Then you may want to know what should be the equation for us to apply, okay? So the basic principle is very simple, all right? The level of fluid will only change when there is a net change of volume inside the tank, or the fluid volume, okay? So inside the tank, okay? Then what will make the volume inside a tank to change? Okay, there's only two reasons. One is we have additional intake of volume, all right? Or we have additional outgoing volume, okay? So intake comes from inlet, outgoing one come from due to the outlet, right? So when the incoming volume is not exactly equal to the outgoing volume, then there's a net change in the volume. The net change in the volume inside the tank will produce variation in the level, right? So mathematical equation is quite straightforward. This is the net change of volume, okay? It could be net change of a volume per unit of time. Then the volume change divided by area, section area of the tank is equal to the level change. So this level change may refer to the level change per unit of time. All right. So this is the basic equation. All right. Then how to calculate, let's say, intake volume or outgoing volume. So therefore, we want to know the average velocity of the flow, okay, of the fluid which enter the tank or which exit from the tank. So we need to know this equation. So actually, the velocity is quite straightforward, okay? So let's say this is a tube of inlet, or this, or it could also be the outlet tube, all right? So when the fluid flow from this position to this position with a certain amount of time, then we have a travel distance from D1 to D2 is equal to D, and the traveling time, let's say, is a T. Then D divided by T, actually it is the velocity for the flow to enter the tank or for the flow to exit the tank, all right? So this is the average velocity, right? So once we know the velocity, then velocity times A, because this is the distance, travel distance times the area is equal to the volume, okay? And then this volume divided by time, then this is the volume change per unit of time. So this is the volume change divided by time, then this is the volume change per unit of time, all right? Then d divided by t is what is the velocity, all right? So then this one times the area, so it's equal to the volume change per unit of time. Then volume change per unit of time divided by A will give you the level change per unit of time. Okay, so these are the basic equation for us to follow. Okay, now I'm going to show you a few examples, and from this example, then you understand, okay, how to calculate the fluid level from the value of related physical quantity, right? In this example, we have intake of fluid. We also have outgoing of fluid, all right? So the intake freeze rate is 1 hour. You will, okay, receive 20 meter cube, okay? Then within 1 hour, the outgoing fluid is 18 meter cube. Then obviously there's a net increase, okay? Within 1 hour, the net increase is about 20 minus 18, all right? Now we want to know, okay, what is the change of a level H within 10 minutes, all right? So, and the sectional area is given to you is 100 meters square, all right? So therefore, we need to know what is the net increase or net reduce of volume inside the tank. Then in this case, there is a net increase, John, all right? So the net increase is the input volume minus output volume, okay? Per unit of time. Now here, let's say we use minutes as a unit of measurement for time. Then here is 1 hour. 1 hour is equal to 60 minutes, all right? So 20 minus 18 divided by 60. Then we get this value of 1/30 meter cube per minute, right? So when within 1 minute, there is a net increase of this amount of volume, okay? Then within 10 minutes, then what will be the net increase of the volume? Should be theta Q times theta T, all right? Then this net increase in volume should correspond to the net increase in level, right? Then let this volume divided by area, sectional area, then is equal to the increase of the height, okay? Because the tank cannot change the diameter, okay? Because the geometry of the tank is fixed, so therefore the liquid level will goes up, all right? So then theta Q is this one, 1/30. Theta T is 10 minutes, all right? Area is 100 meter square, okay? So then 1/100. So then you calculate this one. Then actually this is the unit of a measurement of a meter per minute, okay? And then we can convert it into millimeter. Then we get this value, 3.33 millimeter per minute. So this is the rate change in the fluid level, right? Okay, then this second example showing you that initially the fluid level in tank A is okay, is 5 meter, right? And the fluid level in tank C is 1 meter, right? Sectional area of both tank are the of tank A is 50 meter square cube meter square, okay? And the sectional area for tank C is 45 meter square, all right? And then the flow rate, okay? Because in a separated study, we will, okay, in separated lecture, we will study the measurement of a flow rate. So here, you see we have, we just give you this value. The flow rate is 0.5 meter cube per hour. Now we want to know how long will it take for the level of tanks A and C to be equal. All right. So here we apply this principle of conservation of a volume because we treat the A and the C to be a same fluid system. Okay. Then this same fluid system has a dynamic response. Right. So and there's no external intake of fluid. There's no outgoing fluid to the external system. So therefore, the total volume of fluid is conserved, right? So initially, let's say at the initial condition, the total volume should be equal to the volume inside tank A plus volume inside tank C. So section area times the fluid level equal to the volume. Okay, this is the volume in tank A, this is volume in tank C. Okay, when the fluid level reach the same level, that means the value are equal. Does not mean in the physical space they are at the same level. Okay, so that means when we measure the level of a fluid in tank A, the reference is the bottom of tank A. When we measure the fluid level in tank C, the reference is the bottom of tank C. Okay, so when they reach the same level with respect to their own reference height. Okay, so then this is the remaining volume of the fluid in tank A. This is the new volume of the fluid in tank C. Add them together, they must equal. However, at this point of time, the level in tank A is equal to level in tank C. Okay, so we just name it at this value hash F. Okay, then from this equality, okay, of volume, because there's no leakage of a volume, there's no intake of a volume. Okay, so this is a very important equation. Then we can come out the formula for us to calculate hash F. Okay, because all the value we know, you just put in the value, you should be able to get this result. Okay, so once we know the level, okay, for both tank to meet, okay, to match. Okay, so then we want to know, okay, how long it will take for tank C to reach this value from initial value of 1 meter. Okay, so because when these two levels match, okay, the value is 3.105. Okay, then how long it will take for tank C to reach this level? Okay, so the time, okay, because the variation of height is equal to the net increase in volume times theta t divided by A area. Okay, then we can come out the formula for us to calculate theta t. So this is the formula from here. You see, now we both side divide by theta q, both side times A, then you should be able to get this formula, right? So, and the net increase in the level in tank C, it should be the 3.105 minus initial level, all right? So you put in the value, you should be able to get this answer, right? So this is a typical example for us to, okay, to derive the solution or derive the answer to this question, okay? Here's one more example, okay? So in this case, assume, let's say we have an intake of a volume for tank C1, also intake of a volume for tank C2. Assume the level in tank C1, level in tank C2 maintain constant. Then in this case, we want to know what should be the outgoing volume per unit of time from tank C2. All right, so then the answer should be obvious. Okay, here we for the tank C2, there are two intake. Okay, there's an intake of a volume from this valve. All right, so the intake is a QI2, and also there's an intake of a volume from Q1. Okay, so then Q1 plus this, okay, should be equal to the outgoing one. Okay, in order to maintain this level to be unchanged. Okay, so because this is a variation, okay, from this intake, and then variation from this intake, and then this is a variation from this outgoing volume. Okay, so as long as the outgoing one is equal to the intake one, and the level, the net change in volume equal to 0, then the level will remain at the constant value. All right. Okay, so here is one more example. Now you see, this basically is a transient response of this fluid system. Okay, let's say this is the initial state. Then after a certain amount of time, then you will see, okay, when this fluid system reaches the steady state response, then the fluid level will be the same. All right. So now this is a transient response. Okay. So initial condition is in tank 1, we have this level H1, and tank 2 as this level H2, tank 3 H3. Now we know that the outgoing fluid from tank 1 is 0.2 meter cube per hour, and the outgoing fluid from tank 2 is 0.15 meter cube per hour. All right. So now we ask you to determine what are the level change of a tank 1, 2, 3 within 30 minutes. All right. So we just need to know, okay, what will be the level change rate in tank 1, level change rate in tank 2, level change rate in tank 3, and then we times this time, then we should be able to get the answer. All right. So for tank 1, then we know intake is 0, outgoing is Q12, and then divide by the section area. So then we will obtain the level change rate per hour, because this is a volume change rate per hour. Okay, so negative 0.2 divided by 25, then negative 8 millimeter per hour. Okay, so 1 hour equal to 30 minutes. Then 30 minutes equal to 0.5 hour. Okay, 1 hour will vary negative 8 millimeter. Then half hour is what? Negative 4 millimeter. All right. So then for tank 2, the intake volume is equal to Q12. Outgoing volume is a Q23. Okay, and this is a net change, okay, of a volume inside tank 2 divided by the section area. So that will give you the fluid level change per unit of time. Okay, then 0.2 minus 0.15 divided by this. Then answer is 2 millimeter per hour. Then what will be the change in time within 1/2 hour? Okay, so the answer is this one divided by 2. All right, so that is 1. All right, then for the flow level change rate. Okay, so for tank 3, we only have an intake volume. Okay, so this is the intake volume. Outgoing volume is equal to 0. Then this one minus 0 divided by section area, then get this value 6 millimeter per hour. Then within half hour, what will be the level change? Answer is what? Half of this one, 3 millimeter. All right, done already. Okay. So that's about the indirect measurement of fluid level if we know the value of related parameter. Now our focus is on the study of a physical principle which will enable us to design direct measurement and the sensing system for fluid level, right? So then what should be the popular way for us to follow in order to design measurement and the sensor system for fluid level. Okay, and you may want to know, okay, is it important for us to measure the fluid level or control the fluid level? Actually, the answer is yes. All right. For example, in the petrol station, right, and we have a storage of fuel, right? Then we want to know whether we need to top up the fuel or not. Okay, if we need to top up the fuel, then we must make a call. Okay. For the supplier to deliver fuel. And in the petrol station, you understand the fuel basically is stored inside the tank placed on the ground, right? So this is an underground horizontal tank, okay? So therefore, we need to know, okay, whether we need to top up or not. And for vehicle itself, for example, we want to know the fuel tank is full or empty. all right, or is halfway full, etc. And also inside the vehicle, there's also the cooling water, okay? So we need also to know the level of cooling water, etc. Right? And in industry and in society, we also need to control the fluid level. For example, in the river, okay, we also need to control the level of water in the river or in the sea, etc. And in the chemical plant, then you will see there are plenty of storage tank for chemical. Then we need to know, okay, what should be the level, okay, of chemical inside each tank. And for the industry, which will produce cooking oil, for example, then you see a lot of tank there. Then we need to control the level of oil, cooking oil inside this tank, etc. Right? Then in agriculture, okay, so like hydroponic garden, then you see the supply of nutrition to the plant, okay, it's based on the use of fluid, okay. Then we need to control the level of water, the water with a mixture of nutrition to the plant or vegetable, etc. Right? So the level control of fluid is important. All right. Then we may also have a water treatment plant, okay, to recycle the water. Then you will see a lot of tank for storage of water. Then we need to know, okay, to control the level. So obviously we need to have a sensor, okay, to provide us the direct measurement about the fluid level, right? Then what should be the physical principle for us to know or to follow in order to guide the design of measurement and the sensing system for fluid level? So actually there are many principles, because this is very important aspect of measuring and controlling storage of fluid. This is why there are many inventors, okay, or company, they come out with a solution, and this is why there are many physical principles. So here I'm going to show you three popular one, and these four popular one. These four principles are quite easier and straightforward for you to understand, and also for you to apply in order to guide the design of the measurement and the sensor system for fluid level. All right, and later on I will show you other type of design principle. Right. So principle number one is to convert liquid level, the fluid level, into pressure. So this is a straightforward solution. It's quite easier. Is a simple solution for you to understand. Okay, into the pressure, and we know that the pressure could be converted into DC voltage, and the DC voltage could be measured by microcontroller. All right, so this is a principle number one. Principle number two is to convert liquid level into capacitance, and the capacitance could then be converted into DC voltage, because we have studied the measurement of capacitance. Then this principle should be familiar to you, or this principle should be simple for you to understand. All right. Third principle is to convert liquid level into resistance, okay, and which could be converted into DC voltage. Again, we have also studied the measurement of resistance. Therefore, this principle should be quite simple for you to understand. All right. And the fourth principle is to convert liquid level into buoyant force, okay? And the buoyant force could be converted into DC voltage, right? Because we know when there's applied the force on piezoelectric material, then this piezoelectric material will produce voltage as output again, okay? So this principle should be simple for you to understand and for you to follow. All right, so these are the four principles for you to learn and for you to apply in future in order to guide the design of measurement and the sensing system for fluid level. Right? Then you may want to know, okay, what should be the detail for you to apply principle 1 in order to design measurement and the sensor system for fluid level. So then in this case, we make use of microcontroller because microcontroller are programmable digital sensor of a voltage because the microcontroller, all microcontroller include this digital counter, include voltage synthesizer, include analog voltage comparator. Okay, when the predict voltage match with input voltage on the measurement, then this signal will be generated internally inside the microcontroller, which will stop the counter. Then the remaining value inside the counter should be the transformed value, which correspond to the measurement of voltage. Therefore, we just need to have these two additional modules. The first one is to convert fluid level into pressure. Then second module is to convert pressure into voltage, right? So we have already studied the lecture on measurement of pressure. So we just need to know, okay, how to do this conversion, okay? Once we should be able to get the reading of the pressure, then subsequently we should be able to transform the pressure into readable value, right? Then how to do how to implement the first module, okay, in this design, okay. So the answer is quite straightforward, okay. So basically we make use of a diaphragm, right? So this is a diaphragm. Diaphragm can take in two pressure, okay. So then in this case, we can build up this measurement pipe system, right? So we can, okay, let the low pressure above the fluid, okay, to enter left side of the diaphragm, and let the high pressure at the bottom of the tank to enter the right side of the diaphragm. Then here you will see there's a pressure difference, okay? So this pressure difference is proportional to density of the fluid or liquid, and proportional to gravitational acceleration, and proportional to the level of the fluid inside the tank. So this is a quite straightforward principle for you to follow, okay? So therefore, and then the pressure could be first convert into voltage, and then voltage into computer readable value. Okay, then from this equality, then you see the pressure, the height, the level is proportional, linearly proportional to the difference of the pressure. Okay, so this is one solution. Okay, which consists of converting, okay, the fluid level to differential pressure, right? We can also convert fluid level to gauge pressure, okay? Gauge pressure means let the P1 equal to P0. Now in this case, you see left-hand side of the diaphragm is open to the air. Then in this case, the water, the fluid surface is also exposed to the atmospheric pressure. So this is atmospheric pressure, okay? Then in this case, the measurement should be corresponding to the gauge pressure, right? So, and in a similar way, we can use a diaphragm, okay, to pick up the signal, okay, about the gauge pressure, right? So this is quite straightforward. Then you may want to know how to apply principle 2 in order to guide the design of a measurement and the sensing system for fluid level. Then in this case, okay, so fluid level is converted into capacitance. Once we have output of capacitance, then we can apply the solution learned from the lecture on measurement of capacitance, okay, to complete the design. So therefore, in this lecture, our focus is on the transformation from a fluid level into capacitance, right? Then what should be the solution, okay? So, and here, it is one solution. For example, this is conceptually showing you that we have two parallel plates, and pay attention, each parallel plate is being covered by polymer thin film. This is to provide the insulation, okay? to prevent the short circuit, because for certain type of fluid, the conductivity is very high. Okay, so the current can pass through the fluid. For example, water, the current can pass through the water. All right, so we must prevent, okay, the short circuit. All right, so then in this case, the fluid serve as a dielectric material. All right, so when there are more fluid enter the space between the two parallel plates, the capacitance will increase. All right, so since we know how to measure capacitance, then we can relate the voltage to the fluid level. All right, so this is a way for us to transform fluid level into capacitance, capacitance into voltage, then voltage into readable value. All right, so this is the solution. And in practice, you can design or make use of a capacitor in cylindrical shape. So you see the capacitor wound on the rod, steel rod. So you see the layer, we have an insulator layer and conductor layer, okay? And conductor layer serve as a parallel plate, okay? So physically it's equivalent to the working principle of capacitor, right? So then with this capacitor in cylindrical shape, okay, then you will see the liquid basically serve as a dielectric material, okay? So when this capacitor exposed to more liquid, capacitance will increase, all right? So in this way, we can transform the fluid level into capacitance and then capacitance into voltage, right? So this is an example of implementation for you to apply the principle 2. Then how's about the application of principle 3 in order to guide the design of a measurement and the sensing system for fluid level? Then in this case, we need to know the solution for us to transform the value of a fluid level into the value of resistance, right? So actually there's a clever solution, because we know that most fluid is current conductive channel, so current can pass through. Then we can use this property to serve as a switch. Then in this case, if let's say we have a network of resistor, okay, coupled with a magnetic switch. Okay, by default, magnetic switch is open, because once water enter the space of the switch, actually the water will help the circuit to establish the connection. So we can treat the fluid as a kind of switch. Okay, so we have a magnetic switch, we have an electronic switch. Then we can just imagine we also have a fluid or liquid switch. Just imagine we have a liquid switch, right? Then we have a network of resistor together with a liquid switch, okay? Then the resistance of this network of resistor will change, because based on the state of switch on, switch off, then the total resistance value will vary. Okay, so this is a working principle, very, very interesting working principle for us to achieve this transformation from fluid level into resistance. All right, so then this video basically showing you that you see we have a network of resistor, and actually these are the liquid switch, because it just you have two ends. Okay, once the level reach there, and automatically is a switch on, because water is a natural conductor, right? So then in this case, so it's very interesting for us to achieve the measurement of a discrete value. So actually this corresponds to digital signal, okay? So you can jump to like one bit, another bit, right? So actually it looks like a digital value, okay? So we should be able to measure discrete level, right? And in some application is good enough. For example, inside the vehicle, we want to know whether the level of a fuel inside the tank is 5%, 10%, 15%, 20%, etc. We do not need to know the value now, okay? is 5.0113%. As a driver, we don't care about the the number after decimal channel. It's good enough for us to know, okay, 5% remaining, 10% remaining, 20% remaining, or 65% remaining, right? So many applications is good enough. For many applications, it's good enough for us to know the discrete value of Freed level. So this corresponds to a digital number of Freed level. All right. So then you see how it works. Okay. You see, so the liquid serves as a natural switch. Okay, when it goes down, then switch off automatically. All right. So it's very intelligent design. Okay, so now you see we have a magnetic switch, electronic switch, and the liquid switch. Then in this way we change the resistance inside a network of resistor. So this is a network of resistor channel. Okay, so it's quite straightforward. All right. Then how to apply principle 4 in order to guide the design of a measurement and the sensing system for Freed level. So this one is quite straightforward because we know this property of Freed inside the tank. This property is about buoyant force produced by the Freed inside a container or inside a tank. Therefore, we can leverage on this phenomenon to transform Freed level into force, then force into voltage. Because when force applied to piezoelectric material, then there's output of a voltage channel, right? So then we just need to know, okay, how to convert Freed level into the force. Then we should be able to know, okay, how to measure the force, because we have already studied the lecture on the measurement of force, right? Then how to convert Freed level to buoyant force, okay? So the answer is quite straightforward. So we just have this floating material, right? And then on top, we have this sensing element such as a piezoelectric material, right? So when the level rise, then the amount of displaced liquid or Freed will increase. Then it means the buoyant force, okay, will increase. Then the output voltage should be proportional to the force. Okay, then in this way we manage to transform Freed level into voltage, and then voltage should be directly the input to microcontroller system, right? Oh, all right, so besides these 4 popular design principles, there are many other design principles. For example, you can use a distance sensor, because we have studied the measurement on the measurement of a position, such as a distance. And for example, we can use ultrasonic sensor or radar to measure the distance between the roof of the tank and the Freed surface. Okay, so this gives us this distance. Okay, then the total distance minus the total height of the tank minus the reading from distance sensor should be the level of Freed inside the tank, right? So, and you may also, for example, if let's say we just want to know the discrete location, there's a maximum location, minimum location. There's another interesting method for you to know is vibrating fork, right? So, and when the Freed reach this level, the behavior frequency response of vibrating fork will change, all right? So that gives us an indication about the level of Freed, okay, at this particular location, all right? So, and this video basically shows
the most
you
varied media are filled into and drained from storage tanks every day. Examples are potable water, fruit juices, oils and fuels, acids, brines, or even solids like grain, plastic pellets, or powder. Since these media can have completely different properties, there are different measuring principles to detect them. For example, point level measurement in liquids or bulk solids according to the vibronic principle, called also tuning fork principle. The tuning fork, which John Shore designed more than 300 years ago, served as a basis for the vibronic principle invented by Endress and Hauser in 1967. This principle uses the direct correlation between oscillation and damping in media. Let's have a closer look at how this measuring method works. Vibronic instruments monitor point levels in tanks, containers, and pipes. A sensor, in form of a tuning fork, is excited to its resonance frequency. The vibronic measuring principle in liquids is based on the resonance shift of a piezoelectrically excited oscillation system. There are two different piezoelectric drives, the bimorph drive in standard instruments and the stack drive in coated instruments. The bimorph drive consists of two discs, a piezo and a ceramic disc, which are connected to each other. At the same voltage, the piezos are compressed and the ceramic disc is bent. At different voltages, the piezos expand again. This causes the oscillations of the fork. The stack drive, however, stacks and fixes several piezo discs with changing polarization on top of each other. The application of a respective alternating voltage also causes the piezos to oscillate. As the piezos expand, the membrane is bent to the outside. The ends of the tuning fork, which is attached to the membrane, are pushed apart. As the piezo contracts again, the membrane is bent to the inside. The ends of the tuning forks, attached to it, are pulled together. As the tines of the fork are covered in a tank as the liquid rises, the resonance frequency of the tuning fork changes. The immersion into the liquid reduces the frequency. This frequency change is analyzed and converted into a switching signal. In solids measurement, only the piezoelectric stack drive is used. As the bulk solids cover the fork, the oscillation is damped. This changes the amplitude of the oscillation. The change is analyzed and converted into a switching signal. The vibronic measuring principle of Endress.
Right.
The most.
Okay, so you see there are many principles for us to follow. I guess these four principles that we have studied in this lecture should be good enough for you to apply in future. All right. So after the design of a sensing module, always remember to do calibration module. Okay, it's only after calibration the output from your measurement and the sensing system will be exactly equal to the input of a physical quantity on the measurement. All right, and also the unit of a measurement from the output will be the same as a unit of a measurement from the input. And in particular, we want the Zi to be exactly equal to Xi, and the relationship between Zi and the Xi follow this straight line, which is 45 degrees above the horizontal direction, right? And after calibration, then your product or your system is ready. Then before you sell your product or you let the user to use your product, always remember to do error analysis. All right. So error analysis means you repeatedly doing measurement. Okay, about the value on the measurement. All right. For example, the fluid level, you put the fluid level at a certain level, and then you repeatedly doing the reading, and based on the repeated reading from your sensor, then you should be able to calculate the mean value standard deviation. Then from this calculation, you should be able to know what is the systematic error, repeatability error, accuracy of your sensor. All right. And also try to remember to do experiment by changing the input from small value to big value, then by changing the input from big value to small value. And then in this way, you can do the comparison, okay, between these two sets of reading to see whether there's a gap or there's an error or not. Okay, if there's no error, that means your sensor does not have a hysteresis error. Otherwise, your sensor has a hysteresis error. All right. So remember to do error analysis because these data are needed by your user or by your buyer. All right. That's all for today's lecture. So the key takeaway from today's lecture is for you to understand the basic physics behind the fluid level. And in particular, we have studied the way for us to do indirect measurement of the fluid level. And the key focus is for us to know or to learn these 4 design principles for us to follow in order to guide the design of the direct measurement and the sensing system for fluid level. All right. Thank you for your attention. I'm looking forward to seeing you in the study of next lecture.